Good afternoon, students, and welcome to EJC Online Classroom. I am Yannick Zimnis-Patterson, and I will be taking you through chemistry today. Before we begin, let me sanitize. Please remember that we spend 20 seconds to apply the sanitizer to between our fingers, all over the back of our hands, the palms, and our thumbs. 20 seconds, now we're clean. And guess what, guys? This is chemistry. Let us pray. Almighty God, we give you thanks and praise for life. We thank you, O Lord, that in the midst of a crisis, you are our shelter. We thank you, Almighty God, for Jesus Christ and him crucified and the salvation that is offered to us. We pray, O Lord, that even as we enter this classroom, that you will be our master teacher, that you will govern the teaching learning process, and that the students will understand. We pray in Jesus' mighty name. Amen. Okay, so today we'll be looking at acids, bases, and salts. But before we do that, we're going to look at our verse for today, which comes to us from Jeremiah 31, verse 29. And it says, "In those days they shall say no more, the fathers have eaten a sour grape, and the children's teeth are set on edge." Okay, so what does this really mean? The fathers have sinned, and the children have been affected by it, are reaping, as it were, the sour grapes. And today, we are going to look at some things that are sour. We are going to be looking at acids. Let us look at our objectives. What do we want to learn today? We want to be able to, by the end of this lesson, define an acid in one way, define a base, state at least 3 properties or features or characteristics of acids, state at least 3 properties of bases. We are going to try to identify acids and bases based on their reactions with indicators, and we're going to try to write a few equations based on the properties of acids. Okay, so we are going to begin. What is an acid? An acid can be defined in so many ways. We'll just look at about 3 of them. An acid is a compound which forms hydrogen ions as the only positively charged ions in aqueous solution. So while many compounds will have acid as hydrogen as a part of the formula, an acid is that entity which has hydrogen as the only positive ion. All right, so if I were to look at a simple, very popular acid, hydrochloric acid, HCl, notice that hydrogen is present. If I were to ionize, meaning if it were to be placed in water, dissolved in water, and it were to be ionized, the only positively charged ions present would be hydrogen. I could take another compound that has hydrogen as well, sodium hydroxide. We can see that hydrogen is there, but if it were to be ionized, separated into its ions, the only ions, hydrogen would not form a positive ion here, right? So while many compounds do contain hydrogen, an acid is the one that has hydrogen as the only positive ion when ionized in aqueous solution. Okay, let us look at another definition. An acid is a proton donor. An acid is a proton donor. Okay, so we have in aqueous solution, okay, I'm having a problem there. Okay, so we have in aqueous solution, when an acid reacts with, say, a metal hydroxide, it donates its hydrogen ion to form water. So let us look at the combination of HCl and sodium hydroxide. So we have here sodium hydroxide plus HCl. An acid and a base, as we will find out later, gives us a salt and water only. The salt would be sodium chloride and water. Really, what happens, the hydrogen ion is donated to the hydroxide ion, which comes together to form water. So acids are proton donors. All right. And then, as we have just seen here, an acid is a substance containing hydrogen which can be replaced directly or indirectly by a metal to form a salt. And this is what just happened here. The hydrogen from the acid was replaced or was donated here, and see the sodium ion, which is a metal, has been replaced by the hydrogen, forming water and of course a salt. So that's what we are looking here at, acids. An acid is a compound which has hydrogen as the only positive ion in the aqueous solution. Very good. All right. So we move on. Now, acidity, how acid something is. Acidity is proportional to the number of hydrogen ions present. So really, something becomes acidic because of the presence of the positive hydrogen ions. So hydrogen ions cause acidity. Let us move on. So we're going to be looking now at some examples of acids. Here we're looking at mineral acids. They come from minerals. They are not from living or organic material. And here we have a few of them. I know most of you are familiar with at least one. Here we have hydrochloric acid, as we mentioned before, HCl, nitric acid, HNO3, sulfuric acid, H2SO4, and the phosphoric acid, H3PO4. So for CXC, we really need to concentrate primarily on these mineral acids. There are some other acids that we need to pay attention to as well. They are acids that we find in everyday life. Chemistry involves not just work in a laboratory, but chemistry, which is the study of matter and the reactions that matter is involved in, is all around us. So we might not recognize it, but let us look at some acids that we find in everyday life. All right, so citric acid, which you find in citrus fruits. Citrus fruits like, yes, lemons and limes and oranges. Yes, citric acid is found in citrus fruits. Next, methanoic acid, found in the venom that we would say ant sting, found in the sting, the venom of ants. Next, lactic acid, found in sour milk, right? And we enjoy yogurt, many persons, as a result of the fermentation of the milk. When the milk goes sour, lactic acid is the acid that is produced. Can anyone tell me, let me see a show of hands, of somewhere in the body where we can find lactic acid, and under what conditions? Please comment and tell me where we can find lactic acid in the body. Come on, Burnside, come on, Strawn, come on. Where can we find lactic acid? Very correct. In our muscles, when our muscles respire anaerobically. All right, let us continue. Ethanoic acid or vinegar, also known as acetic acid, is found in vinegar. And of course, there are persons who like pickles and escovitch fish and so on. This is a vinegar. Okay, then we have tartaric acid found in grapes, and we can go back to our text or verse for the day, which says that the fathers eat the sour grapes and the children's teeth are set on edge. When in Jamaica we say we teeth are nedgy, but when our teeth are set on edge, something is irritating, something is unpleasant. No, it is the tartaric acid in the grapes that gives that sharp, sour taste that causes our teeth sometimes to be set on edge. And of course, the Bible likened these sour grapes eaten by the fathers as sin, which has irritated the lives of their children. Okay, and finally, something we are cautioned not to partake of, we have carbonic acid found in sodas. All right, so we're moving right along. We're going to look now at some properties, some features, traits or characteristics, whatever way you want to put it. We're looking at some properties of acids. Again, I'd like you to participate. What are some of the traits? What are some of the traits of acids? Some things by which acids can be identified. If I were to ask you, how would you identify a Seventh-day Adventist? Many people would speak about Sabbath keeping or not eating pork and lobster and so on. What are some of the features? We are Bible-believing people, yes? Yes, so what are some of the characteristics? And most importantly, we are anxiously awaiting the coming of Jesus. So let us look now at some of the properties or characteristics of acids. How can we identify acids? All right, so we identify that vinegar is an acid. It has a sharp, sour taste. Next, that's one feature. Acids are corrosive when concentrated. All right, does anybody know what that word corrosive means? Let me know quickly, please. Nobody? All right, so a substance which is corrosive damages metal and skin, right? It's harsh. It burns away on metal and human flesh and other things as well. But this just to show you how dangerous acids are. But this is in its concentrated state before it is diluted by adding water, or after it is added to water. All right, so first, acids have a sharp, sour taste. It's corrosive when concentrated, turns damp blue litmus red. That's another feature, and in a little bit I'll be showing you some of these reactions. Incidentally, we could also use this characteristic to define an acid. An acid is any substance that turns damp blue litmus red. And we will explore what litmus is, and we'll see some of the changes. Finally, acids have a pH value of less than 7. Of course, we'll be looking at the pH scale, and we'll be identifying the position of the acids and the bases on the pH scale. Okay, so we have looked at some physical characteristics. We're going to look at some chemical reactions now of acids. There are a couple of them. I'll just be looking at a few of them today. All right, the first one we have here, acids react with reactive metals to form a salt and hydrogen gas. Let's go again. Acids react with reactive metals, and that's very important, reactive metals to form a salt and hydrogen gas. So basically we could say an acid and a metal gives you salt and hydrogen gas. An acid and a metal gives you salt and hydrogen. Now we have an example here, and then I'll be giving you another one on the board. Let us look at this one. It says sulfuric acid, H2SO4, did you remember that one? Plus zinc gives us The salt being zinc sulfate and the hydrogen gas. So let us look at this again. The acid, being the proton donor, passes on its the zinc, being more reactive than hydrogen, displaces hydrogen and leaves it out in the cold, and the zinc forms a bond with the zinc sulfate, forming the salt. All right, let us look at another example. If you will go with me to my whiteboard. All right, so we said an acid and a reactive metal gives us a salt and hydrogen gas. So because we just used sulfuric acid, I'm going to use another one. All right, so I have here HNO3 plus a metal, and the product should be a salt and a hydrogen gas. All right. Can someone please identify for me this acid? What is the name of this acid? Very good. This acid is nitric acid. We are reacting potassium with nitric acid, potassium being a very reactive metal. Now again, we'll see that because potassium is very reactive, it displaces hydrogen and takes its spot. So we have now that this potassium displaces hydrogen and a salt is formed. The name of the salt is potassium nitrate. And of course, we have hydrogen gas. Please bear in mind, students, whenever we're writing an equation, that the equation must be balanced. I'm sure you remember that. So the number of each element must be the same on both sides of the equation. So if we were to pay attention here, we have 2 hydrogen atoms here, but only 1 here. So we put the coefficient in front of the acid to balance it. Now I have 2 hydrogens. But now I need to do something else to balance my equation. Now everything is balanced. 2 hydrogen, 2 hydrogen, 2 nitrogen, 2 nitrogen, 2, 3, 6 oxygen, 2, 3, 6 oxygen, and 2 potassium atoms, 2 potassium. Very good. All right, so we said when we react an acid with a very reactive metal, we have forming a salt and hydrogen gas. Let us look at another property of acids. When acids react with a base forming, we have salt and water only. Let me get that slide up for you. So an acid and a base forms a salt and water only. Let us look at our example. Our example here is the one I gave you before. Hydrochloric acid plus sodium hydroxide gives us the salt, sodium chloride, and water. So an acid and a base gives us salt and water only. So we're going to look at another example of another equation that illustrates this characteristic of acids. And just in case you have forgotten, how do we identify bases? Bases are either metal oxides or metal hydroxide. So anything that has an oxide or a hydroxide in it, it is a base. All right, so let us look at another equation which demonstrates this property of acids. Acids react with bases to form a salt and water only. All right, so we have here calcium hydroxide. Notice the name, calcium hydroxide. And again, I said, once the name, the compound has in it an oxide or hydroxide, it is a base. All right, but we get to that a little later on. So if we react a base with an acid, let us look at, we looked at, okay, let's go with HCl. What will the products be? Of course, please remember, you are commenting below and saying, helping me as we move along. Okay, so an acid and a base gives us salt and water. Acid being what? HCl, which is hydrochloric acid, and our base being calcium hydroxide. Very good. All right. Now, if we react these two compounds, what will the products be? Of course, we said it must be what? A salt and water. Often I say, put in what you know. And what everybody knows is water. You know you're going to get a salt, and you know you're going to get water. So put in the known first. Put in the water. If you're not too sure what the salt is going to be, you can remove the water. And you see what you'll have left behind is calcium and chlorine. So we know that the name of the salt is going to be calcium chloride. Bearing in mind its valency, the formula would be calcium CaCl2, calcium chloride. Again, when we react an acid and a base, the products are salt and water only. Is our equation balanced? No, it is not. How can we balance it? By putting a coefficient to the left of or in front of the compound. All right, let us see if it is now balanced. One calcium, 2 oxygen, 2 plus 2 hydrogen, that's 4. 2 2's 4 hydrogen, 2 chloride ions, 2 chloride ions. So now our equation is balanced. So here we have another characteristic of acids. When they react with the bases, they form salt and water only. Next, we're going to move on to another characteristic. If you look on the board, you will see acids react with carbonates and incidentally hydrocarbonates as well to form a salt, water, and carbon dioxide. Let's look at that again. Acids react with carbonates and hydrogen carbonates to form a salt, water, and carbon dioxide. All right. The example we have here is HCl. What's the name of that acid? Very good. Hydrochloric acid. And a carbonate, notice the CO3 there, calcium carbonate, will come together to form a salt, water, and carbon dioxide. The name of the salt? Calcium chloride, water, and the CO2. Very good. Can we look at another example? Can we look at another example? I am going to use not calcium carbonate, but sodium carbonate. So I have here an acid, which will be sulfuric acid, this time, plus sodium carbonate. What will the products be? According to our characteristic of acids, we say that the products are going to be salt, water, and carbon dioxide. Again, if you're not too sure what the salt is going to be, take out what you are sure of. We are positive that among the products, we will have carbon dioxide and water. So let's put those in. So we leave the space for the salt. We put in the water, H2O. We put in the carbonate, the carbon dioxide. So we have now, all we need to do is to put in the the salt. If we were to take out the carbon dioxide and the water, what is left? Sodium sulfate, Na2SO4. So acids react with carbonates and hydrogen carbonates to form a salt, water, and carbon dioxide. Is our equation balanced, by the way? It seems so. Yes, it is. All right, so let us move on. And a little later on, I will give you a few others to do. All right, another feature of acids, they react with hydrogen carbonates. I'm just showing you this equation. As I mentioned before, acids react with hydrogen carbonates to form a salt, water, and carbon dioxide. Our example here, sulfuric acid plus, can anybody tell me the name of this hydrogen carbonate? Very good. This is sodium hydrogen carbonate, and the products again you'll see sodium sulfate, water, and carbon dioxide. Very good. So we have been looking at some of the properties of acids. We said that acids have a sharp, sour taste. They are corrosive when they are concentrated. They turn damp, blue litmus red, and they have a pH value of less than 7. We also identified some chemical reactions that acids take part in. And of course, this is by no means the final list, but these are just some of the reactions that acids take part in. First of all, we have acids react with reactive metals to form a salt and hydrogen gas. We said that acids neutralize bases to form a salt and water. Acids react with carbonates to form a salt, water, and carbon dioxide. Acids react with hydrogen carbonates to form salt, water, and carbon dioxide. Of course, there are many other reactions like an acid and a sulfide, an acid and a sulfite, so many other reactions, but we are just looking at a few this afternoon. Let us move on now to bases. What are bases? Bases are said to be the chemical opposite of acids. The chemical opposite of acids. As indicated before, we said that if we want to identify a base, we can look in its name or its formula. The name, we look for oxides or hydroxides. If they are present, we know that they are bases. So bases are metal oxides or metal hydroxides. And here we have two examples, calcium oxide, CaO, and sodium hydroxide, NaOH. Let us move along. Bases can also be defined as proton acceptors. So if when acids react with the bases, the hydrogen from the acid combines with the hydroxide or the oxide from the base to form water. So bases are proton acceptors. Again, we can also define bases in terms of their reaction with litmus. We said that acids turn blue litmus red, and now we can say bases turn red litmus blue. All right, so here we have another term, alkalis. What is an alkali? An alkali is a base which dissolves in water to form a solution that contains hydroxide ions. Basically, we could say that an alkali is a soluble base. An alkali is a soluble base. Okay. Okay, so now we're going to look at the properties of alkalis, the properties of the soluble bases. And here we have, first of all, alkalis have a bitter taste. Now, you should know from day one, we don't taste anything in the laboratory, right? But alkalis have a bitter taste. Like acids, they are corrosive when they are concentrated. Many persons believe only acids are corrosive, but if you think about some cleaners that you use in your bathroom, lye or sodium hydroxide, caustic soda, very corrosive, will damage your skin, will damage metal. Alkalis have a soapy feeling, right? And they, as I said before, they turn damp red litmus blue, and now they have a pH greater than 7. All right, so we have identified what bases are. We have defined them. Now, how can we distinguish, after saying all of this, how can we differentiate an acid from a base? Well, we can do this by using indicators. And an indicator is a substance which is one color in an acid and another color in an alkali or in a base. So we're going to be looking now at some of these. We're going to be looking now at some of these indicators and how acids and bases react. So we have some examples here. Litmus is an indicator. It's either red or blue. In an acid, it is red. In an alkali, it's blue. Methyl orange, it's red in an acid, but yellow in an alkali. Screened methyl orange, or screened really means mixed, right? So it's methyl orange with another dye. Screened methyl orange is red in acid and green in alkali. And phenolphthalein is colorless in an acid and pink in an alkali. So I'm going to move over now to my workstation, and we're going to be identifying, we're going to be looking at some of these reactions. All right, so here I do not have all the indicators listed above, but I have a few of them, and we'll be using. So here I have phenolphthalein, I have screened methyl orange, and I have red and blue litmus. We'll be looking at how some of the acids I have here and bases, how they react in these substances. Again, indicators can be used to identify and differentiate acids and bases. All right, so here I have as well universal indicator or pH paper. The truth is, the indicators that I mentioned before, they can be used to identify if something is acidic or if something is basic. But the universal indicator, pH paper, or if you want to use a pH meter, will tell us how acidic or how basic a substance is. All right, so I have a couple of acids here. I have CH3COOH. Does anybody know what this is? I know you do. Right, this is ethanoic acid. And you find ethanoic acid in what? Everyday food? Very good, in vinegar. Okay, so since we know it is acidic, we should already know what the product or what the change is going to be. But I'm going to use, first of all, red and blue litmus paper. We said that acids turn blue litmus red, and the bases turn red litmus blue. Let us see if this is true or people just making this thing up. All right, so I'm going to put both red and blue litmus in the vinegar that I just poured in the test tube. All right, so red and blue. What did we say acids do? Acids turn blue litmus red. Okay, so let us look at this now. I actually placed 2 pieces of litmus, one blue and one red, and now here we have 2 red litmus papers because acids turn blue, litmus red. I can even add a base to this and change this pH back to this litmus paper back to blue. Let us see if that will work. Okay, so because we know that bases turn, alkalis turn red litmus blue. All right. Can we see that? So that means it's true. Acids turn blue litmus red, bases turn red litmus blue. Remember we said they are chemical opposites. And did we see that happening? Excellent. All right. So that's one indicator. All right. Can we look at another indicator? I have here screened methyl orange. Remember, whenever you're working in the laboratory, if you make a mess, and that will happen from time to time, you clean it up immediately. All right. So we have here now screened methyl orange. What is the color difference we said? In an acid, screened methyl orange is red, but in a base it is green. So I actually poured sodium hydroxide. So what color should this be now if I were to put the screened methyl in it? All right. All right, very good. So it is green. Screened methyl is actually green in an alkali. Suppose I were to add an acid until the acid is neutralized, the base is neutralized, and it becomes overwhelmingly acidic. Do you think there will be a change in the indicator? All right, let's see. So I'm adding hydrochloric acid, HCl. Beautiful. All right, so again, we said that indicators are dyes, are substances which have one color in an acid, but another color in a base. All right. And the final one I have here is phenolphthalein. All right, so I'm going to be adding phenolphthalein to a fresh test tube. Phenolphthalein, it is colorless, just as if it were water. But if I were to add an acid, what color would it be? Please remember, if we were to refer to our chart, phenolphthalein is colorless in an acid, but it has a beautiful pink color in a base. So I'm going to use a base. So I have here, okay, I'll use the sodium hydroxide. Beautiful, beautiful. And I think I'd have to use a whole lot of acid to neutralize this, but let us see if we can, if there is space in our test tube. So phenolphthalein is pink in a base, but it is colorless in an acid. Yes? Okay, very good. So acids and bases have different colors when they are exposed to indicators, right? And the indicators that we have used here are phenolphthalein, colorless in acid, but beautiful pink in a base. We used the screened methyl orange, which is green in an alkali or base, but it is red in an acid. We used blue and red litmus. Litmus is red in an acid, but blue in a base. Let us move back to our desk for a minute. We're going to be looking at the pH scale. All right, so pH, often described as the potential or the power of hydrogen, is a measure of how acidic or alkaline a substance is. So if you want to know if something is an acid or something is a base or an alkali, we refer to the pH scale. Now the pH scale is like a number line which extends from 0 to 14, with 7 being neutral and less than 7 acidic and greater than 7 alkaline. So we'll notice that pure water is said to be 7 on the pH scale, and vinegar 3.2 on the pH scale. Say sodium hydroxide will have a pH scale of about 14, right? So the pH scale shows us how acidic or alkaline these substances are. If we look at the pH scale here, it shows us different colors. So we can use numbers or we can use colors to identify the acidity or alkalinity of a substance. And it extends from red to violet or purple. All right, let us look at this chart now, which has a couple of things, a couple of everyday substances. So we start with battery acid, which has a pH of 0. We don't want to go near to that. Stomach acid 1, lemon and vinegar, lemon juice and vinegar juice 2. We have again neutral pure water. Then we can look at mild detergents at 10. At 13, we have bleach and the oven cleaner, very, 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 very alkaline. And of course, drain cleaner, caustic soda, has a pH of 14. So if you want to know not just if something is acidic or basic, but how acidic or basic these substances are, we refer to the pH scale. And if we want to identify the exact pH of a substance, we would have to use universal indicator, or what we call pH paper, or a pH meter. All right, so we're going to move again to our workstation. This time we are using universal indicator. So again, the litmus paper told us the phenolphthalein, the screen methyl orange, that guess what? This is an acid, this is a base, but it really don't tell us how acidic or basic it is. So we would refer now to our pH paper, which not only says, oh, this is an acid, but it tells us, well, you know what? Stay away from this, because this is very acidic. Or it says, this one is very basic. All right. So if I apply the substance to the pH paper, I will use my pH scale right here as a guide to indicate what the exact pH is. Now, I know based on it that it is an acid. Yes? It is an acid, but how acidic is it? Is it a strong acid or is it a weak acid? All right, so if I align it on my pH paper, I'll see that this has a pH of 1. Not only is it acidic, but it is very acidic. It is a strong acid. So you know what? Stay away from this one. Again, I could apply the pH paper to something that is alkaline, and it would tell me not only that this substance is alkaline, but how alkaline it is or how basic it is. So I have here some calcium hydroxide. Calcium hydroxide. I've added it to my pH paper. Again, I don't know, I know it is a basic or alkaline, but how basic or alkaline is it? I put it beside my pH scale and I see that it has a pH of 12, meaning it is relatively basic as well, very a strong base as well. So while other indicators tell us whether something is acidic or not, the pH paper tells us what? The degree of acidity or alkalinity. All right, before we wrap up, I have some colorless solutions here. And I wish I had one of you here to come and help me. Want to come and help? Okay, we are going to try to, they actually look like they're water, don't it? But we're going to use our indicators not only to identify, but we can distinguish which is an acid and which is a base. And which should I use? Should I use phenolphthalein? Should I use screen methyl orange? Should I use litmus? What should I use? Okay, I will go with screen methyl. And we said that the color difference is what? Screen methyl orange is red in an acid, but it is green in an alkali. All right, so I'm just going to add them, a few drops to each. So that one is what? What is that, sir? It is an acid. Of course, we are, oh, so that one is a base. Very good. Acid, base, acid, base. So we have an indicator helping us to identify whether something is acidic or basic. Okay, let's go back to our slides. And since I've been working at the workstation, I have to sanitize again. Clean off those hands. We don't know what is there, do we? All right, in between the fingers, the back of the hands, the palms, and the thumbs. All right. Again, we're told to do this for 20 seconds. Very good. All right. So let us look at a question now. Excuse me. You are given aqueous solutions numbered 1, 2, 3, and 4, which have the pH values listed below. All right, so 1 has a pH value of 2, 2 has a pH value of 7, 3 has a pH value of 8, and 4 has a pH value of 13. Based on what we have looked at before, can we classify, can we identify these substances as strong or weak acid, neutral, strong or weak base? All right, let's go again. So if we were to look at the pH scale, so if we're looking at our pH scale, we'd see that a pH of 2 would be what? A very strong acid. But a pH of 7 would be what? A pH of 7 would be what? Neutral. What about a pH of 11? Weakly alkaline. And of course, a pH of 13 would be a strong alkaline. Okay, very good. So let us recap what we did today. We identified acids, bases, acids and bases. We defined them. We said an acid is any substance that has hydrogen as the only positive ion in aqueous solution. We identified bases as either a hydroxide or an oxide, metal hydroxide or metal oxide. We identified acids based on their characteristics as sharp sour, having a sharp sour taste, as turning blue litmus red, as having a pH lower than 7. We identified bases as having a bitter taste, a soapy feel, turning red litmus blue, and having a pH greater than 7. Of course, we identified, based on the pH scale, that pure water would have a pH of 7. Excellent. We also found out from the Bible that while the fathers sinned, the result of their sin was that the children's teeth were set on edge. In those days, they shall say no more, the fathers have eaten a sour grape, and the children's teeth are set on edge. Why won't they say that anymore? Because the children would have turned to God, that we would no longer be suffering from the effects of our parents' sin, but we would turn ourselves, our sins, over to God. Thank you so much, students, for participating. Thank you so much for giving me a bit of your time. This has been EJC Online Classroom. Today we looked at acids, bases, and salts in chemistry. I am Yannick Zimnis Patterson, and thank you for your time. Please remember that the King's way is the best way. Have a good afternoon.